Welcome back to the IoT course. Today we continue our investigation of IoT application areas, and we will first look into healthcare. So how can IoT applications help with healthcare, and give some examples. And then we'll take a look at something you might have already seen or might be using already, smart home applications for the IoT. So we're still in part one of the course, application areas, and this is the second lecture in this part. So we've seen this graph of trends in IT application areas already, and healthcare, as we've seen, is not in the top, but in the middle of these application areas. Whereas what we consider to be smart homes, so buildings, has seen less importance in the last years, though maybe because a lot of homes are already equipped with smart home technologies, at least to some extent nowadays. So today we're going to focus on healthcare and smart homes or smart buildings, but of course there are a large number of other application areas, and in the next lecture we'll also summarize some of the other application areas. And as always, we're going to discuss challenges, features, and in parts also infrastructure components, and give examples of the use cases and of devices in this lecture. So, healthcare and well-being. The question we need to ask ourselves is, what functionality can we use that is provided by the IoT in healthcare and also in personal well-being applications? So analysis have found out that there are three main user groups in healthcare applications for the IoT. The first is doctors or physicians. So they want to keep track of patients' health, even if the patients do not show up in person. So, for example, if you have some long-term treatment, you actually want to have data about how this long-term treatment works. If you have people with a medical condition, you want to monitor that medical condition, like heart rate, for example, over a longer time without having people in the hospital just for doing these investigations. And of course, sometimes patients obviously don't really want to keep to what the doctor prescribes. So it could also be used to track the patient's adherence to treatment plans. And of course, if there's any immediate medical attention, so if you have a precondition with a heart problem, or elderly people who are prone to fall and hurt themselves. So here IoT can also help physicians and also, of course, in this case, emergency services to figure out that there's the person requiring help, and using additional technologies like GPS integrated in devices, also figuring out where this person is right now to send help as fast as possible. Now, IoT is also of use in hospitals. So in hospitals, you often have the problem that medical equipment has to be moved around the hospital. So without any IoT or tracking support, you would probably be constantly searching for some of the equipment, especially for rare or more expensive stuff. So here, IoT applications combined with, for example, localization support can help to track the real-time location and also the state of medical equipment. IoT can help to analyze and control deployment of medical stuff, so they can figure out where persons working in your medical team are currently located inside of your hospital, and telling them to be relocated in case of an emergency, for example. And an important thing, especially, of course, nowadays in times of Corona, is hygiene monitoring. So really figuring out if certain pieces of equipment have been disinfected, if cleaning has been done regularly, and so on. And finally, there's a third user group, which might be a bit more controversial, and this is health insurance companies. So, health insurance companies, like car insurance companies, also want to have a tighter control or a tighter overview of what their customers are doing. So, for cars, you probably have seen offers like, oh, let us install a GPS device in your car that continuously sends information out to the car insurance provider. And using this, the insurance provider can figure out if you brake uh, regularly, if you speed too far, too much, if you drive dangerously, whatever. This is, of course, uh, yeah, well, quite invasive considering your privacy. So, nevertheless, this is something that happens in car insurance, and obviously, health insurance companies want to do the same with their patients. So, their incentive is obviously to lower their expenses for healthcare. So, they want to have, well, what they call incentives for customers to using and share health data. So essentially, the offer is that you get a well bit of a reduction in your monthly fees for healthcare in countries where you have to pay your healthcare fees yourself, obviously, and also that you should be able to validate claims through data captured by IoT devices. This is a significant intrusion into privacy, so I'm not sure if I would love to see this implemented in the future. So, in addition, of course, you've seen all these devices offering personal well-being. So, fitness trackers, devices like these smartwatches that can control your pulse, your blood oxygen levels, and so on. So, all of these devices are not necessarily connected to healthcare providers, doctors, or hospitals, but they help you to plan your exercises, to stay healthy, to supervise your training and to plan your training. But it can also help to coordinate group exercises like a whatever jogging tour through the park with a couple of people in the morning. And as I said, you can supervise your own health parameters like heart rate, glucose level, or even mood monitoring. You can have elderly persons supervised in a bit. Like if people are unable to really help themselves, they can get help in case they need it without there being a permanent requirement of supervising them. And now there are a number of common challenges, especially for medical devices that can be implanted or worn on the body. Size and energy are critical because you don't want to carry a large device, or if you need an implant, of course, it has to fit inside your body. And the energy provisioning is also critical because, well, you don't have a power line nearby, obviously. Medical devices should be reliable. So, especially for things like implants, you don't want to apply surgery every couple of months in order to exchange a defective device. That's absolutely unacceptable. And of course, this is very personal data that's collected and processed here. So, you want to have data protection and security. So let's look at some examples from the healthcare area. And one common problem is for patients suffering from diabetes. So diabetes patients require monitoring of blood glucose levels, and this is required to determine their required insulin injections. So usually this is a manual process, or this has been a manual process where you take a blood sample, you apply it to some sort of test sheet or test paper, and then you get some information out of it. And according to this, you can actually plan when you need your next insulin injection. This is, as I said, manual, this is analog, this is maybe horrible for people who can't see blood, and this is also an error-prone process. And if a patient then makes an error or is careless, then the patient's life can be endangered significantly. So what we would want here is a device that allows us to monitor uh, the glucose levels in your blood continuously, so especially automatically, also providing a history, and if you want, also a supervision by a physician, so that when you go to your next appointment with the doctor, all of your data is already available. Here again, of course, we have some concerns regarding data protection. So this is done by a device that has a number of sensors. So obviously you need a sensor for glucose levels and maybe additional body parameters that just influence the way your body reacts to this. So for example, body temperature and also environmental data like the outside temperature. And this glucose monitoring device that's shown on the top right-hand side here is monitoring all these parameters, and it has a connection to a smartphone. This can be a Bluetooth or an RF connection here. And the smartphone, again, has a cloud gateway, for example, to store all your health data or to just forward it to your doctor. Obviously, you want these devices to be energy efficient. You don't want to be remembered of charging them every day. And here, energy harvesting, like in that reference we show here on that page, is enabled by energy efficient operation. And in the table on the right hand side, you see that in the lowest possible configuration, this is using a small ARM Cortex NRF transmitter, so a chip that is using a ARM Cortex by Nordic Semiconductors, plus an additional Atmega controller handling the I/O. You can get the required current in operation down to half a milliampere at only 2 volts. So this is a feasible application for energy harvesting. So which components do you need here? You have a microcontroller as shown in the bottom of the slide in the middle, and this microcontroller is connected first obviously to a power management device, which then in turn is connected to whatever form of energy harvesting you're using, maybe temperature based, maybe based on retrieving energy from body movements and so on. Then you have a number of sensors like temperature and glucose sensors. The temperature sensors are connected directly to the microcontroller, so they can capture body temperature and outside temperature, whereas the glucose sensor is somewhere in a part of the body where it doesn't interfere with your daily life. So here you have an inductive link receiver, so you have a wireless connection to the microcontroller controlling all of this, and in turn this performs wireless communication to the smartphone you usually carry around with you. So obviously, what's described here in this paper that we reference here, number one, is a research prototype that considers the use of energy harvesting, but these devices already exist in the real world. And one example for a commercial system is developed by Ericsson. It's called Actiste, and this is, as we've seen before, not only a product, so a device that you use, but it's combined with a service. And this is providing both under and over levels of glucose, so hypo and hyperglycemia in your body. So what you have here is a blood sampling device, a blood glucose meter, and even an insulin pen for administering the insulin injections in one device. And the objective here is to reduce the error. So what the developers wanted to do is they wanted to minimize the number of actions that is needed by a patient for diabetes control. So that's why you have combined functions for sampling, measurement, and injection. And of course, you have a companion smartphone app that not only informs you when an action is needed, but it also gives you insight into how your lifestyle maybe impacts blood glucose control. So you can actually check more or less immediately after you've eaten something what the impact of this food on your blood glucose levels is. And you can also download reports of all the treatments, so you can determine opportunities to improve blood glucose control. So essentially to improve your lifestyle considering your medical condition. Now, a completely different area still related to healthcare is another personal device worn on the body, and this is a hearing aid. So hearing aids exist for quite a number of decades already. At first, they have been analog devices that had to be configured, especially to the hearing loss problem of a patient by a specialist. And the thing is that these traditional hearing aids, no matter if they're analog or if they're already digital, containing a small signal processor to do signal processing and amplification, they're still problematic with some external audio sources like telephones or TVs. So what would be required or would be interesting is an adaptation to changing hearing characteristics of the environment, but also to a change in your hearing yourself. And obviously this, while the first hearing aids were worn on the body, like you had a large box with a large battery worn on the hip, and then a cable going to the hearing aid in your ear. Modern hearing aids are just things that fit in your ear, like wireless headphones, more or less. And obviously, you want size constraints, so it has to fit in your ear somehow. And you don't want to charge it every couple of hours, so these devices have to be energy efficient. And obviously, they need to process signals from the outside, change them, and provide them to your inner ear. So essentially, you have to perform real-time signal processing, which requires quite a bit of computational power. So this is a trade-off between energy efficiency, real-time, and size that you have to find in order to build a viable device. And the nice thing about this is if you build a IoT connected hearing aid, you can actually have additional information. So very many headphones already provide audio noise cancellation. You can have something like personal sound zones. So, for example, you don't want to be disturbed or the sound is turned down when you're in a special room in your device. You can have audio broadcasts. So if you have a hearing aid and this is connected to your stereo system, you could have audio uh, just directly transmitted to your hearing aid and then formed correctly so your ear is able to hear it in the way you want without requiring additional headphones. And the same about alerts and sound streaming. So this is an example of a structure for an IoT connected hearing aid. So we see the components in the graphics on the lower right-hand side. So in the middle, we have a processor, and this processor is connected to a number of components. The first component, obviously, is the analog front end. So you have one or more microphones. These microphones create analog signals. These analog signals have to be conditioned. They have to be converted to digital signals to be processed by the CPU in the system. So this is what's happening in the analog front end. Then, of course, you have a processor. This processor has quite a bit of volatile memory, so RAM. So this stores samples usually to be processed and also maybe runtime data. This performs signal processing and also controls the tasks of the complete system, just communication over wireless and so on. And this is the heart of the system that performs all this signal processing. So we need digital signal processing functionality in order to enable our hearing aid to perform real-time signal processing. Of course, you also have an output stage, which is what transmits to your ear. And here you usually use a technique called pulse width modulation as a digital signal synthesis and amplifier technique. Then you have some user interface. So you might have simple controls on your device, like a volume control or a push button or a sensor. And of course, you might also have an interface to your smartphone in order to control more details. And this is done using wireless communication. And this wireless communication then can also be used to send data, for example, from your stereo or from your telephone in order to enable you to use the hearing aid as an, sort of a headphone adapted to your hearing. So the interesting thing when it comes to IoT is as soon as you have some sort of wireless or internet connectivity in your hearing aid, you can use it for more functionality. So especially combined with a smart city environment, IoT hearing aids can be quite interesting. So what can you do? You can send information. For example, you can, if you stand at a bus stop here, then you could have the next departure times of the upcoming buses automatically transmitted to your hearing aid. The same, of course, in a train station or whenever you require some sort of information. Uh, you could also automatically receive warnings to your hearing aid. For example, you could get information about a pedestrian traffic light or about construction areas or about alarms that go off in your neighborhood and so on. All of this can be enabled by near-range communication, for example, Bluetooth Low Energy. And back when I was at TU Dortmund, we did some early work for trying to do some smart information integration. Back then, without IoT hearing aids, but with location-based services. And if you're interested in that, you can find it at the URL below. So, hearing aids with IoT connectivity can give quite some benefits to their wearers. And the overhead is not that high since you require a powerful processor and quite an amount of resources in the hearing aids already. And I think this will be a technology that will be very interesting, especially as our society is growing older and older and hearing problems are becoming prevalent even in younger people nowadays. But of course, these devices were mostly external without the consideration of the glucose sensors. Sometimes you also need medical sensors implanted in your body. You've seen things like pacemakers, obviously. This is one obvious example where you need to implant a device in your body in order to enable your health and living. In general, medical sensors that you implant in your body serve to monitor and control body parameters and functions. And in addition to pacemakers, we can have the glucose sensor transmitters that we already have seen. We can have oximeters, we can have pH sensors, or even nerve and brain stimulators, for example, for patients suffering from epilepsy. So here we have even more challenges concerning energy, size, and also communication. So obviously, when you implant something in the body, it should stay there for a long time. It should work for a long time, so you don't have to service it regularly. So you need to provide it with some sort of energy. And in order to work with the little amounts of energy you have available, it has to be very energy efficient. Obviously, it also has to be very small. So you have to be able to implant it somewhere without impeding your other body functions. And you have to find a way to communicate. Now, you probably know that a human body consists mostly of water, so like 70%, I guess. And this is a problem when you do standard wireless communication, for example, over the standard 2.4 gigahertz band. So you might have noticed that microwave ovens also operate in the 2.4 gigahertz band, and that very often there is a setting in your Wi-Fi that reduces microwave interference. And microwaves work that way, microwave ovens, because they're able to heat up the water molecules at exactly a frequency of 2.4 gigahertz, where all these free network frequencies that your Wi-Fi and Bluetooth use are also located. So this is a problem. And wireless networking using Bluetooth Low Energy or Wi-Fi would be impossible, and it would also be very problematic considering the amount of energy these would use. So for implanted sensors, researchers actually went a different way, and they implemented something we call wireless body area networks, or W bands. And this actually uses the human tissue as part of its transmission channel. So you have very low voltages, very low currents. Obviously, the whole human body, like nerve stimulations in your brain, operates on electrical signals already. So you can imagine this is possible. Now, obviously, you won't get a high amount of throughput. So essentially, I've seen devices that can transmit like 10 kilobits per second, and some can go up to 500 kilobits per second. And of course, you have connections to devices that have more compute functionality. So again, you might have a smartwatch or a phone that is connected to your implanted medical sensor. So you can check your condition, you can check the condition of the devices, and so on. And obviously, using these wireless body area networks, you can also connect multiple sensors and multiple devices that have to be implanted in different parts of your body and enable them to communicate. Now, the overall structure of such a medical sensor system implanted in your body is shown on the lower right-hand side, left-hand side. So here we have a number of sensors connected using the wireless body area network, and then in turn connected to applications on external devices. Now the problem is, how do you actually install these devices? Of course, one thing would be surgery, and that's a very common way for devices that have to be implanted permanently. But sometimes you want a temporary sensor solution. So as shown on the lower right-hand side here, there are also developments already where you have ingestible sensors. So they're like a pill, and the hull of the pill is usually made of some sort of sugar, which dissolves inside of your stomach, for example. And this way releases a sensor inside, which is able to communicate and, for example, measure the acidity in your stomach in case you have ulcers or problems with stomach cancer or whatever. And these devices are obviously very small. So what we show on the top right-hand side here is already one of the bigger devices. You see the background is a US 1 cent coin. And this device is just maybe 1/3 of the size of this coin. And you see the left-hand part is mostly what looks like an empty PCB. And I think that's where some communication, like an antenna, would be implemented here. Now, there's one big problem with especially implanted medical devices. And this problem is that these devices are supposed to work for many years or even decades to support the patient's life. And as I said, of course, you don't want to undergo surgery every couple of months or a year to update your device. That's something that will probably be pretty unacceptable. So one big problem here is not only reliability, we've talked a bit around about reliability of devices before, but especially obsolescence. Of course, as with most medical devices, there's a commercial entity, a company behind this that produces and supports these devices. So what actually happens when this company goes bankrupt or decides not to support a specific product anymore? And here's an example that was in the press just last week. So this is very advanced technology built by a company called Second Sight Medical Products, and these are what we call bionic eyes. So these are optical sensors that connect to your retina in case your retina is somehow damaged by genetic factors or by accidents and is able to inject electrical information into the signal path going from your eye to your brain. And this way, it enables patients who are blind because of retina destruction or problems to actually see. Now, what they're going to see is not what you expect as a person to see if you have normal eyesight. So what you can expect to see is shown on the lower left-hand side. So for example, a person who's wearing this glass-like device that's connected to the retina is standing in front of a door, and this picture the person sees is shown on the top right-hand side of that small picture there. So essentially you see a door frame and an open door, but this is still better for navigating, for example, through rooms than seeing nothing at all, obviously. So it's a very low resolution view of the physical environment, but still very useful for people who require this. Now, the problem is that the company building these things went bankrupt in 2020, and the products are now unsupported. So, in case your device breaks, you're unable to get fixes anymore. And the company was obviously very secretive about the contents of their devices, like they didn't publish any schematic diagrams, repair information, or software source code. So, whenever something breaks, you cannot just ask an external service provider to fix the thing for you. That's something you use with smartphones. You don't have to send them to your original manufacturer, but you can have them repaired independently. So the company actually refused to release any information on this. So there are patients who cannot use devices anymore after a defect or a problem. And of course, if people have to undergo, for example, a head surgery, then because this is an implanted device, then doctors would need information about the actual functionality of these devices, maybe how they can be temporarily removed, how power provisioning works to these devices in order to perform surgery on persons. And this information was never available. So this missing information really led to lots of problems with patients using this, even though they paid a lot of money for it. So this is a very problematic thing, and of course this is very invasive. So the way it operates is shown on the lower right-hand side. So essentially you have an electronic component connected to your retina that's able to inject signals there. This in turn is connected to your glasses, and these glasses then contain a camera, obviously, and then you have a link to a video processing unit that's worn on the body that enables the video processing of devices in order to convert the camera video stream coming from the outside to signals appropriate and compatible with your vision system. So this is a big problem, not only for this device, this was just in the press recently, so it was a good idea to demonstrate it here, but in general for any sort of device. And of course, if your life or your well-being depends on it, then this is really, really critical. Now, let's talk about some nicer things for a change. So, smart home is a topic you've all seen, so you can buy smart home components not only in specialized electronic stores, but you can find them in any supermarket from now and then nowadays. And there's a large amount of different devices out there, from smart light bulbs to systems supervising your house to window shades and so on. So the general idea of implementing smart home technology is that should be able to equip your home with sensor and actuator technology that serve a number of applications. So the first thing that's really interesting is energy saving, not only for large office buildings, but also for your home. So you could automatically turn on and off your light and your heating on demand. So whenever there's no persons in a room, you don't need to turn on lights. You can have the heating turn off before you leave the house and have it turn on automatically as soon as a sensor or some information is transmitted to your smart home system that you're coming home. So your house is nice and warm without having the heating running all day. And of course, you can also monitor external weather conditions. So if you figure out a snowstorm is incoming, you can turn the heating on in advance. So it's nice and cozy at home. Another thing is safety, so you can protect your home from, for example, fires. So you can have smart smoke detectors. Traditional smoke detectors just, detect smoke and, release noise. This only helps when you're inside the house and you can hear it. Smart smoke detectors obviously are connected to the internet using IoT technologies and can then, for example, send information not only to you on your device, but maybe also automatically forward it to the fire brigade in order to, react as fast as possible. Another application area is security. So you want to, uh, well, avoid burglars entering your home. So you want to have intrusion detection. You want to have remote surveillance, but you maybe also just want to figure out, like, oh yeah, the postman is outside and I'm not at home, but I wanted this package right now and I want to have it when I return home. So you can communicate with the postman using a camera in your door. You can figure out it's really the postman and then you can maybe let the postman in automatically, or you can tell the postman or postwoman, obviously, where to deposit a parcel that's to be delivered without having to pick it up manually or having to wait for a redelivery. And of course, there's a number of comfort functionalities included in smart home. So you can have door sensors, you can have door cameras, as we mentioned already, or maybe automatic window blinds that close in the evening without you having to walk around the house and lower all the window blinds automatically. So all of this, as usual in IoT devices, has to use a number of sensors and actuators, and all of these are in turn connected using networks again. So we have near range networks. These can be Wi-Fi networks, but these can also be specialized near range technologies. And we'll take a look at a number of them in the next part of this course. Something like Zigbee, for example. And of course, you usually want a gateway to the internet. So when you're not at home, you can control the functionalities. You can check what's going on in your home when nobody's there. So one example for a smart home application is the Nest thermostat. So the Nest thermostat is a smart device which is designed to control a air conditioning system for your whole house. And this is smart because it uses data learned from your behavior in order to automatically control the air conditioning and heating in your house. So this connects to your home or office network and interfaces also with what is called the Nest Cloud. So you can do a remote control from your smartphone when you're not at home. So this Nest thermostat is something you just attach to your wall, like a normal thermostat for your heating. And this, in addition to the normal heating controls shown on the lower right-hand side, also has a Zigbee wireless module for communicating with other devices in a Nest network. For example, things controlling your air conditioning and a large number of other devices in this family. So what's interesting is that this device uses a form of machine learning. So when you install the Nest thermostat in the first couple of weeks, you need to set it manually because the device doesn't really know which temperature levels you're comfortable at. So essentially, by setting this manually, the device records the temperatures and the times and the day of week, and maybe even the environmental conditions from the outside to provide a reference data set so the device can figure out later on if there's a certain condition, like it's cold outside and it knows you're coming home in 20 minutes, it can turn on or turn up the heating already. So the Nest thermostat can learn schedules, temperatures, and behaviors of people living in the house. In turn, it can also enable energy saving when nobody is at home, and this is determined using built-in sensors, and it can also use phone locations. So if it figures out using Bluetooth that your phone is in the house, then obviously it makes sense to turn on the heating, and if it can't find any of your phones in the house, then it can cool down the house to save energy. And this device is already a couple of years old, and what's interesting is that this actually provides quite a lot of computing power for such a small device. So you have this round LCD display in the middle, and you use, well, a touch screen to control it. So you have a dial, like on old iPods, for example, to change values, and you also have a menu system on a color display. And this actually uses a dual processor setup, so all the user interface and wireless functionality is provided by a Texas Instruments system on chip with a single core ARM Cortex A8. So this is running Linux on 64 megabytes of RAM. So this is quite a powerful IoT embedded device, comparable to the first Raspberry Pis, more or less in computing power. And for controlling all the I/O, so the embedded controls and sensors, this is using an additional microcontroller. This is also by ARM and Cortex M3, which has considerably less memory, for example. And this controls driver circuits, this controls temperature and humidity sensors, so everything you need to control the climate inside of your home. Another example, which is pretty common nowadays, is video surveillance of your home. So when you're at work or on holidays, you want to ensure that there's no intruders in your home. So this obviously has security focus, so you can monitor video and also audio streams when you're away. And in order not to have a camera running all the time, you have smart cameras nowadays that have built-in functionalities, for example, for motion detection, and of course they have internet connectivity in order to send you a stream to look at to figure out what's going on in your home whenever, for example, there's some motion detected, and then you can use your smartphone or browser application to watch a live stream and also to listen to audio. This intelligent camera functionality is quite advanced nowadays, so you don't only have motion detection, you can also detect if it's really a person moving in the house, who is unexpected, or if it was just the sun creating a change of image on the camera. And this is obviously done to avoid false alarms, because you don't want to have false alarms every time that the sun shines through the window and just changes the picture seen by the camera. Now, obviously, these devices require high bandwidths to stream video, so they require Wi-Fi or fixed wired Ethernet connection. And I've seen data sheets that give data rate that's required for live video in 1080p with like 6 to 10 FPS, which is enough for supervision. And this uses compression to compress this down, but this still requires 1 to 2 megabits per second. Obviously, you only need this when you're actively looking at a picture from your remote device. But then, of course, in this case, you need this bandwidth to be available in order to really watch the video seamlessly. And smart light bulbs, of course, are a premier example of smart home applications. So when you buy a light bulb, and here we show the example of an IKEA troll-free light bulb, this is available for around 100 kroners. And there was a German magazine, like linked here in this reference number 11, that actually disassembled this light bulb to actually check what's inside. So how much electronics can you get for like 100 kroners? And that's pretty interesting. So this light bulb provides you not only with manual control, so you have wireless switches or wireless dimmers that can communicate with your light bulb to turn it on or to change the color temperature or the intensity of your lighting. This is done by a number of 12 LEDs. So you have 6 cold and 6 what we call warm white LEDs, and these signals can be mixed and controlled in their intensity using pulse code modulation. You can also integrate this into your whole smart home system using a gateway, and this gateway connects, for example, to a number of sensors that can control lighting. For example, if you have motion sensors, then if some motion is detected, it can automatically turn on the lights. I mean, you've seen this functionality already, maybe in public buildings. So if there's bathrooms with automatic lightings, you don't want to have light switches in a bathroom because that's a major transmission medium for bacteria or viruses. So you want to have the lights automatically turn on whenever there's somebody in the bathroom, and you want them to automatically turn off when nobody's in the bathroom anymore in order to save energy. So this interconnection is enabled by automatic control, and this gateway that's available then connects your smart light bulbs to whatever other things are available on an Ethernet or wireless network. So the interface from the light bulb to the gateway is done via Zigbee, and the whole functionality of this light bulb is actually quite high powered by another ARM Cortex-M microcontroller of the M4 family, which includes wireless functionality already. So this is running at 40 megahertz and has 256 kilobytes of flash and 32 kilobytes of RAM, and that's just for a light bulb. So this is pretty interesting because you wouldn't have expected to get so much electronics for just 100 kroners. And of course, this also seamlessly integrates into a whole family of smart home devices, like automatic window blinds, like motion sensors, like dimmers, and so on. And since these things are produced in large numbers, you can actually get them for quite low amounts of money nowadays, which is interesting. So we've seen a number of applications already. So of course there's many more smart home applications, but we assume that many of you who are interested in IoT have bought one or the other device already, and it would be interesting to hear about your experiences, how well these devices work, how compatible they are with each other, how good they interact, how reliable they are. The medical application sector is a sector that is an upcoming and sector that's increasing in relevance here, especially since the requirement for medical attention is rising quite a bit. Smart home applications are already quite common nowadays. They went down in price. So the big problem with IoT and smart homes is actually how much work do you have to invest to get it to work? How easy is it to set up these things? Do you need to be a computer science specialist in order to set up the network and these devices? And this in turn will control and influence the adoption of these devices in smart homes. So the benefit for all these devices, no matter if it's medical or smart home, is of course that in the best case we have interoperability. So these devices can not only connect to specialized applications, these devices can interact with each other. So for example, we can connect medical devices to smart home and city environments. We can, for example, have this hearing aid integration that we've seen with a home or a city network to provide, for example, audio streaming or information provisioning. Now, all this requires common protocols, so we'll take a look at common protocols in an upcoming section of this course. So these are, together with common network technology, the basis actually for transmitting information between your IoT devices. So this is all for today's lecture. Thanks for listening. And in the next lecture, we'll summarize the application areas and then do a review of common problems, challenges, and benefits we can have from different classes of IoT devices in different applications. So thanks for today, and until next time. Bye.